In this second module of Chapter 5 on population growth rates, Module 5.2, I will cover doubling time and the population growth outcome of different types of mixtures, of subpopulations, and of sequences of growth rates. Doubling time. The expression for the geometric increase of population size to time t is n at time t equal n at time 0 times 1 plus r raised to the tth power, where r is the fraction of increase per unit time, and n0 is the initial number in the population. The time it will take for the population to double, acronym dt, in size, that is when 2 equals the number at time t over the number at time 0, is the solution to the equation 1 plus r raised to the tth power equal 2, and t equal double time equal ln2 divided by ln 1 plus r. Since ln 1 plus r is approximately equal to r, except at high values of r, this equation further reduces to dt, that is doubling time, equal ln2 over r. More generally, a population will increase by n-fold according to the equation time to increase n-fold equal ln n divided by r. For example, if r equals 0.1, then n values of 3, 10, and 100 will yield increases by 3-fold in 11 days, by 10-fold in 23 days, and by 100-fold in 46 days. Population growth, subpopulations, and sequence. There are two ways to compute the growth of the total population at time t, denoted n. One sums the growth of independent populations, and the other computes growth rate as the average rate across subpopulations. Consider two examples where population A is increasing by lambda of A equal 1.1, and population B is increasing by lambda B equal 1.4. So case 1, independent populations. In this case, each subpopulation grows independently of the other, and the total population is simply the sum total of the numbers in the two different populations. N at time t equal n at time 0 for population A, lambda A raised to the tth power, plus the number at time 0 in population B times lambda B raised to the tth power, where n0A and n0B denote the numbers in the respective populations at time 0. Suppose each population begins with a single individual, then projections to time t equal 30 for this situation is the number at time t equal number at time 0 for A, lambda A raised to the 30th power, plus number at time 0 for B, lambda B raised to the 30th power, equal 1.1 raised to the 30th plus 1.4 raised to the 30th equal 24,218.9. So case 2, average growth of two populations. The second way to compute growth rate of the total population at time t is to compute the average of the respective growth rates, and that is lambda equal the square root of the product of lambdas A and B, equal 1.24. The projection for this second case is number at time t equal number at time 0 lambda equals 634.8. The nearly 40-fold difference between the results of the two types of projections in these two cases shows that separate projections of subpopulations always yield a greater total population growth than projecting the average of the growth rates from each subpopulation. Sequence of growth rates. Population growth can vary through time, and the temporal sequence of growth can be computed. For example, if the finite rates of increase of a population are 1.1, 1.8, 1.2, and 1.5 at times 0, 1, 2, and 3 respectively, then starting at t0 with n at time 0 equal 25, the number of individuals at time 4 will be number at time 4 equal the product of n at time 0 and lambdas 0 through 3 equal 89.1. Note that the geometric mean of the four finite rates is the fourth root of the product of the four lambda values, which equals 1.374. And that the product of the initial number of 25 and this geometric mean raised to the fourth power is also 89.1. This is equivalent to the outcome for the projection of the N4 using the separate finite growth rates. This numerical example illustrates a general principle about population growth that varies through time, and that is that the resulting rate of population growth for any temporal sequence is the geometric mean. This ends Module 5.2 and sets the stage for the next module on the derivation of stable population models.